A quadratic function is a function of the form y equals ax squared plus bx plus c, where a, b, and c are constants and a is non-zero. As we will see, quadratic functions can be used to model situations arising in business and economics. Consider the following example. Miracle Dirt produces and sells bags of soil used for gardens. The company can produce up to 200 bags per day with daily fixed costs of $375. When Q bags are produced on a certain day, the variable cost per bag is given by the linear function v equals negative 0.01 Q plus 4. Miracle Dirt can sell up to 200 bags daily according to the demand function p equals negative 0.04 Q plus 13, also a linear function. We will use this data to derive the profit p as a quadratic function of the output q. We'll graph the function and determine the quantity that maximizes the profit, and we'll determine the break-even points. The profit of a business is by definition equal to its total revenue minus its total cost. The revenue function is equal to P times Q, price times quantity. Since we're told that the demand function is given by P equals negative 0.04 Q plus 13, this gets substituted in for P. Now we consider deriving the total cost function. Cost is equal to the fixed costs plus the variable costs times Q. In this case, the fixed costs equal $375 and the variable cost is negative 0.01 Q plus 4, which gets plugged in for V. Then we subtract costs from revenue, multiply everything out, and collect like terms. Finally, we get that the profit function equals negative 0.03 Q squared plus 9Q minus 375. This is a quadratic function. Since at most 200 bags can be produced and sold, the domain is between 0 and 200. Comparing this to the general form P equals AQ squared plus BQ plus C, we can learn some information about the properties of a quadratic function and a parabola as they relate to the coefficients A, B, and C. In particular, the coefficient A tells us the shape of the parabola. If A is negative, the parabola opens down, and if A is positive, the parabola opens up. In our case, A equals negative 0.03, which is negative, so the parabola opens down. This means that the graph attains a maximum value. This maximum value occurs at the vertex. The vertex is exactly the point that tells us the quantity that the profit is at a maximum. The vertex is given by the ordered pair h, k, where h equals negative b over 2a. So in our case, we get negative 9 divided by 2 times negative 0.03, which equals 150. That is, 150 bags of soil will give the maximum profit per day. So the corresponding profit is K equals the profit evaluated at 150. This equals $300. So we plot the vertex at 150, 300. Now another important feature of a parabola is where they cross the horizontal axis. Since the vertex is in the first quadrant and the graph opens down, the graph will hit the q-axis in two spots. These q-intercepts are the break-even points, since it gives the q values where the profit equals 0. So we set profit equal to 0 and we solve for q. To make the leading coefficient 1, I'm going to divide every term by negative 0.03. By inspection, we can factor this as q minus 50 times q minus 250. This gives q equals 50 and q equals 250 for the break-even points. Alternatively, you can use the quadratic formula. By knowing the coefficients a, b, and c, we can find the roots by using the formula q equals negative b plus or minus the square root of b squared minus 4ac all divided by 2a. It is sometimes more convenient to represent a quadratic function in its vertex form, y equals a times x minus h squared plus k. In our case, p equals a times q minus h squared plus k. Having the shape of the graph A and the vertex h comma k will give the rule of correspondence for this vertex form. In our case, we have p equals negative 0.03 q minus 150 all squared plus 300.